Have you ever really wondered how an AI model learns? How it goes from just seeing tons and tons of data to creating something completely new? Well, it's not magic, it's math. And today we're going to pull back that curtain and look at the core probability concepts that are the absolute foundation of modern generative AI. I mean, this is the question, right? How does a machine, just lines of code, go from seeing a huge data set of images or text or whatever to developing what feels like a real understanding of the patterns hidden inside all of that stuff? So, to get our heads around this, we're not going to start with some crazy, massive neural network. No, we're going to build something way simpler, a model whose only job is to figure out where the land is on a world map. This simple example is going to be our guide through some really powerful ideas.
All right, so where do we even begin? Well, before our model can find any land, it first needs a map. We have to define the entire world it's allowed to play in.
Think about it. If our model is looking for land, we have to tell it where to look. We've got to define the entire space of possible locations we could ever ask it about in the first place.
And that idea right there leads us straight to our first big concept, the sample space. It's just the complete set of all possible outcomes. For our map model, the sample space is every single point of latitude and longitude on the globe. A point in Tokyo is in the sample space, so is a random point in the middle of the Atlantic Ocean. They're all valid possibilities.
Okay, so we've defined the boundaries of our world. We have our map. Now, how do we start describing the interesting stuff, the actual continents that exist inside it?
We've got our map, our sample space, but that just tells us what's possible, not what's probable. So how do we teach the model which points are likely to be land and which are likely to be, just water?
And the tool we use for this is called the probability density function, or PDF for short. Think of it as a function that assigns a probability score to every single point in our sample space. Now, to keep our model really simple, we're going to define our PDF as just a box. If a point on the map is inside that box, it has some probability of being land. If it's outside the box, the probability is 0. Simple as that.
So, we've decided our model is a box. But which box? A little one around South America? A huge one covering all of Asia? There are basically infinite possibilities. We need a structured way to search for the right one.
And this, right here, is the core problem. You can't just tell a computer, find the best box. It wouldn't know where to start. We need to give it a much more systematic way to search than just trying random rectangles all over the globe.
The solution here is something called parametric modeling. Instead of searching through an infinite sea of totally unique models, we define a family of them. And every single model in this family can be described by just a few simple knobs or parameters. We use the Greek letter theta to represent this whole set of parameters.
So what are the parameters, the knobs, for our box model? It's just 4 numbers: the latitude and longitude for the bottom left corner, and the latitude and longitude for the top right. That's it. That's our theta. With just those 4 numbers, we can describe any possible box on our map.
Okay, this is great. We now have a whole family of potential models, basically every box we could possibly draw. Which leads us to the very obvious next question. How do we figure out which one is any good? We need a scoring system. Given some real data, let's say the coordinates of a few dozen cities, how can we measure how well any given box explains where those cities are? We do this with a super important concept called likelihood. And notice the way it's written. It's a function of our parameters, theta, given the data, d. And that is a critical distinction. We're not calculating the probability of the data. We're using the data we already have to score how plausible our model, our box defined by theta, actually is. So here's how that works. Imagine our data includes the city of Paris. Now, if we test a box that only covers North America, well, it couldn't possibly have generated our data, right? So that box gets a likelihood score of 0. But a box that does contain Paris and all our other cities, well, that's a plausible model, and it gets a positive likelihood score. Now, technically, likelihood is calculated by multiplying the probabilities of all our data points together. But multiplying tons and tons of tiny numbers between 0 and 1 is kind of a recipe for disaster on a computer. It can lead to errors. So we use a clever math trick. We use the log likelihood. Instead of multiplying all the probabilities, we add their logarithms. It's way more stable, and it leads us to the exact same best model.
Okay, so we've got our family of models, and we have a way to score them. We're ready. Now we can put it all together to find the single best one.
The technique we use is called maximum likelihood estimation, or MLE for short, and the name really says it all. It is the process of estimating which parameters are the best by finding the set that maximizes our likelihood score. We are searching for the one best box out of all the possibilities.
And this is what that goal looks like in math terms. We want to find theta hat. We call that theta hat, which is our best estimate for the parameters. We find it using argmax, which is just a fancy way of saying find the argument, the specific value of theta, that results in the maximum possible value for our log likelihood function. For our map, this means finding the smallest possible box that still contains every single one of our data points.
Okay, let's make the big connection. This is the aha moment. Our goal was to find the best 4 parameters for a simple box. Our method was maximum likelihood estimation. Now think about a huge AI model. The parameters aren't 4 numbers. They're the billions of weights in its neural network. And the process we call training, it's just a massive, incredibly complex version of MLE, an algorithm searching for the set of weights that best explains the data it was shown. It's the exact same core idea.
So we've built this entire foundation using a simple box model. And it worked great, but this leaves us with a final, really crucial question. The real world, with all its images and language and music, is infinitely more complex than a simple rectangle. So how do you build a model, a probability density function, for something that complex? Answering that question, well, that's what takes us from this simple example to the incredible generative models that we have today.